So I'm going to give a talk that's much more technically inclined. I won't mention AI in it, so I apologize to anybody who is really looking to check all three talks off the AI docket. But the title of mine is Architecture of a Next Generation Object Storage Device in the Panasas File System. And I'm going to be concentrating on the how and why on the engineering front from the parallel file system perspective. So first, I'll start with the background. I assume most people here are at least remotely familiar with Panasas from a parallel file system perspective, but I'll be digging into what's an object storage device, how do we use it in Panasas file system. Then I'll move on to why we were significantly motivated to completely redesign our OSD in Panasas and kind of juxtapose our old OSD software stack against the new one in doing so. Third, I'll go into the goals that we had in this redesign, provide 2 exemplary challenges we ran into and how we solved them, and then complete with some performance results that are early, but I felt necessary for such a technical talk. So background first. An OSD, basically you will have in any parallel file system that leverages OSDs 1 or more directors, up to hundreds, and 10 or more OSDs if you are using object RAID, frequently up to thousands. These are our main data storage targets. Basically, clients will write and read directly to these after navigating the metadata that they need to gather from the director. In our case, these expose an iSCSI and RPC interface. The iSCSI side deals with the data, the component data, whereas the RPC side allows us to manage and check the health of the OSD. We use object RAID, which is a superset of erasure coding, to basically splice up our files and directories and send these over the wire to each individual OSD. This is our unit of failure domain. So we will have many OSDs within a blade set, which is our failure domain, and then each OSD will only have one component of the file on it at any time. And finally, each OSD has its own internal file system, which is critical because we are a snapshotting file system and we need to maintain copy on write semantics within the OSD because it would be expensive to do so at a higher level. So how does this OSD fit into the broader Panasas file system? Because we use object RAID and erasure coding to stripe these things across a variable number of OSDs, as you can see on the right side there, we get nice scalability with IOPS and with bandwidth in doing so, and that's only achieved by getting the metadata out of the way. This isn't a especially new thing. We've done this forever, essentially. It's a key part of the underpinnings of our parallel file system, but I'm just kind of providing some background into how the OSD fits in. So as I mentioned, copy on write in the last slide, this is one of the OSD's main responsibilities and one of the biggest complexities. We have to track this copy on write across snapshot groups in order to efficiently be able to say, based on an object where most of the I/O is flowing to the live most object, we have to be able to say, well, what's changed since the last snapshot or the snapshot before that, etc. They also participate as one of their other big responsibilities in scale-out reconstruction. So obviously, if you're using erasure coding or RAID in any way, at some point reconstruction will happen when you lose a drive or an entire OSD, and that is an OSD is our atomic unit of reconstruction at this time. Read and write proceeds to n-1 OSDs unless you've replaced the failed OSD, in which case we're reading from n-1 and we're going to n OSDs in the write phase. So the 3 great architectural complexities of an OSD, since you have some background now and you can kind of conceptualize how they're used, what are the biggest things that we care about as a parallel file system vendor when we're doing development on them. First of all is copy on write, which I've kind of already covered fairly thoroughly. Snapshot chain management, which is the collection of a series of objects over time through snapshot groups. And importantly, making sure that those snapshot chains stay intact as you move objects from OSD to OSD as part of rebalancing, reconstruction, or a series of other background tasks. If you get all those 3 right, and getting them right is easy, but getting them done right and efficiently is very difficult, then you actually have a really powerful unit of storage to base your parallel file system on. So with that background behind us, let's look at some of the reasons why we were motivated to completely rebuild this from the ground up for this release, the ActiveStor Ultra release. So starting with our classic OSD software stack, since we can kind of drill into that atomic unit of storage in Panasas, we start at the top. So right underneath our iSCSI layer, we have a command queuing layer. This does some command validation, session management with the clients, up to thousands of clients, and queuing of those iSCSI commands for tens of thousands of iSCSI commands that can come in at a time. Beneath that, we take all these iSCSI commands and form tasks around them. These tasks basically allow us to, some of the iSCSI commands will be related to one another or have dependencies on one another, and we'll kind of put that all together into a single task before we send it to lower layers in the OSD. The object orchestration layer is where a task is started to execute and is looking to do work on one or more objects at a time. We provide our core component object API at this level, provide some RPC handling for health management of the OSD, deliver attributes, change snapshots, take snapshots, delete snapshots, and do all of our log management at this point. And finally, once you get down to the real media, we have our proprietary FreeBSD-based OSD copy on write file system in this classic OSD software stack that we've split in between SATA SSDs and SATA hard drives. In our blade-based platform, which is the platform most people have seen over the last almost 2 decades we've been in business, this has been basically split in a way such that the data of each object goes into the hard drives, whereas metadata and very small files, or even the very head of each file, will go into the SATA SSD for quick access. While this is a perfect architecture when it was originally invented, it's been over a decade since we really went back to the whiteboard on this, and it was time to do so. This was due to 4 areas of significant technology changes we've seen since that time. First of all, being that the open source copy on write snapshotting file systems were finally viable as an underpinning part of our OSD. So maintaining our own, which is quite difficult and time intensive, was less critical. Second, my Tropicana example here, if we look at hard drives back in the early 2000s compared to today, and you compare the straw as if it's the bandwidth in and out of a hard drive to the orange itself, which holds the orange juice or the data in a hard drive, that's changed dramatically. Just the ability to get data in or out of a hard drive is ridiculous today compared to at that time. It takes approximately 80 times longer now to get data in and out of a hard drive to that time. And these are using hard drives that we shipped at that time and some of the hard drives we ship now. If you were to have a straw, which is now less than a pixel in this example wide, and actually plug it into the 16-inch orange, you would have to drink approximately 9 gallons of orange juice to get all your OJ out. So tiering, going to that last point, tiering within the OSD between all the different media that's available today is even more critical than it was before when we used SSD. Third, commodity off-the-shelf hardware is similarly finally viable for us. We've been designing and delivering our own proprietary hardware since day one, from the sheet metal up, because nothing at the time really served our need. Now they do, and that's really exciting for us because we can essentially redirect some of that engineering and effort we put into developing our own hardware into additional parallel file system features and functionality. It also greatly expands our ability to kind of work with different networking technologies that were difficult to do so before because they were so specific, like IB or OmniPath natively. Fourth and finally, operating system and distribution independence. So what I mean by this is, since we're moving to commodity hardware and we're leveraging some free and open source software under the hood instead of doing proprietary things at the OSD level, we needed to become way more independent about the OS and the distro we were working with. And so that motivated us designing an abstraction layer to really make our parallel file system portable. So what's not changing is the external interface or APIs, and this is really important. This means basically any user of Panasas that has enjoyed the usability and reliability of PanFS won't have any major change to their workflows. That is acting the exact same way. The only thing the external system will notice is that our OSDs are significantly faster, approximately an order of magnitude. So the Ultra project, what goals do we have in the OSD redesign? So goal number one, which I just alluded to at the tail part of our motivations, is complete API compatibility with external users of the OSD. One thing I didn't mention is that this allows us to run both our classic and prime hardware in the same exact realm as the new Ultra hardware, despite them being so different. So those top tiers, the command queuing, task prioritization, and object orchestration layer, stay exactly the same. The realm software basically just represents different images of the new hardware platform so that sysadmins know exactly what it looks like. Goal number two, COTS, environmentally friendly platform as the foundation for our OSDs. So I spoke about COTS, but regarding environmentally friendly, we're moving away from lead-acid batteries to NVDIMMs for our caching solution inside the OSD when it comes to power fail. We've always been really aggressive, even well before anybody really cared about this, about caching inside of an OSD so that if your working set size fits in RAM, you can go extremely fast. We solved that with a lead-acid battery in the back of a shelf, basically for our entire history, and now we're able to move, last year we were able to move the director functionality onto NVDIMMs, and with Ultra we're moving also the storage component to use NVDIMMs for power fail. Goal number three, wider and taller OSDs. So what does this mean? Wider means you have way more hard drives per OSD to get better bandwidth and better capacity per CPU and RAM. Taller means more tiers. We're seeing, even from the last talk, we're seeing an increasing number of different media that allows different tiering for different types of workloads, and we try to manage that all for you within the OSD. So we want to be able to leverage as many of those tiers as we can inside, so we have to support tall OSDs. Goal number four, optimize storage for metadata and data. This is probably one of the most fundamental architectural changes we made with Ultra, and it goes like this. We noticed that when we had some customers that had extremely heavy metadata workloads going at the same time as extremely heavy data flow workloads, they would compete with one another sometimes. Now, we already segmented metadata off to a separate side on the SSD, but if they were accessing very small files, for instance, they might hit the SSD, or if they were just moving along fast enough in the metadata, they might also slow things down. And so what we said was we need to have completely discrete physical as well as completely optimized data structures to house these very different things so that your interactivity with the system doesn't slow down even though you're pumping many gigabytes per second into each OSD. So on the metadata side, we basically selected a advanced database, and we accelerate that using NVDIMM for transaction logging, which coalesces into an NVMe SSD, which gives us the ability to do intelligent querying, faster transactions, and consistent performance since it's not interacting with the data side, which is the free and open source CAL-based file system that we use all three tiers actually, NVDIMM, flash, and hard drives to accelerate. Goal number five, 5 out of 6 here, so almost done. Modular design entirely in user space. Since we had our own proprietary hardware and file system before, we had a lot of tentacles that made it very difficult to make changes in a rapid way. And we knew when we moved to commodity hardware, there would be a big push to have a broader variety of products in our portfolio. So by leveraging a modular design when we were rebuilding things, this basically allows us to move and future-proof ourselves against changing free and open source software and very different platforms that might disappear since we're relying on somebody else to produce it. And you can see on the right side, that kind of shows our entire software stack inside of OSD, albeit at a very basic level. The red obviously being the hot stuff on NVDIMM, the orange being the NVMe SSD, the left side of the CAL file system being small files on SATA-based SSD, and finally the many hard drives for the bulk of the data on the right, bottom rightmost. And finally, maximize performance and minimize performance variability, the latter being really the key goal. That one, the latter part, was really achieved mostly by goal number 4, where we split up the metadata and data, but there was an equally important goal we had where it involved zero bottlenecks. So if we go back to the orange example where hard drives have just changed so drastically, I might juxtapose this to some of the solutions you see out in the field that basically have a tub of drives, 60, 80, 100, behind a single CPU, a single network pipe. That only makes that straw and orange problem way worse. And so we knew we wanted, in redesigning this from a physical and from a software perspective, to not make that problem any worse. So our CPU, our network, and even our controllers, we've assured that they don't go any slower than the aggregate of the hard drives can, or the NVDIMM, or the SSD within each of our OSDs, so that we're not making that bottleneck any worse than it already is. So 2 challenges we ran into. There was numerous, but there were 2 that I felt were interesting to talk about for this, this forum in this redesign. So since we're way wider, 3 times more hard drives in our specific design, and taller, we're tiering between 4 tiers rather than 3 inside of each OSD. How do we make sure that we're still power fail protected, especially since we've gotten rid of the lead acid battery, and without sacrificing any performance? So as I mentioned, we're splitting up our metadata and data, but importantly, we're taking our database transaction log and we're housing it on a fraction of the NVDIMM and allowing that to coalesce whenever it gets extremely busy down to the NVMe. This gives us the ability to absorb a lot of metadata churn without ultimately, especially to the same object, without ultimately this resulting in burnout of our NVMe SSDs or slowing them down. On the data side, we're using the remaining large fraction as an intent log for writes, but we're doing it in a kind of novel way. So what you might imagine doing or solving this problem is basically sending all of your writes asynchronously to the NVDIMM and then allowing that to trickle them out to the hard drives afterwards. This vertical setup works somewhat, but it is at odds with each of the open source file systems we looked at, because you're splitting up these writes into very small chunks instead of letting the Linux kernel basically aggregate these into large bandwidth friendly writes. And so what we do instead is these are at basically the same level. So when you do a synchronous write to your intent log, you're doing an async write just through the normal Linux buffer cache to the underlying free and open source file system. This allows the Linux kernel to do what it does best and basically push massive bandwidth to the underlying hard drives, and we only ever leverage that intent log if we actually run into power fail. That's never flushing down in any way, shape, or form under normal operation. So challenge number 2, instantaneous scalable snapshots. We had, as I mentioned, we developed our own FreeBSD file system for our past OSDs that did snapshot support quite well, but it wasn't instantaneous and it had a cooldown time of a couple minutes. So we wanted to make sure that ours were instantaneous, had zero cooldown, and we could get to the point where we had many thousands of a snapshot within the same volume, unlike what we can do today. So since the local file system we selected can support that, how do we make sure we map that to the metadata side of our parallel file system or within the OSD without sacrificing some of the performance we got out of the local file system? So fundamentally what we did was leverage the reality that most objects won't change between snapshots. Especially when you're talking about petabytes of storage, you're just not going to hit every single one of those objects in between every snapshot. To do this, we basically maintain a couple data structures that allow us to index into the snapshots very quickly and without major overhead to the OSD. We also perform zero updates to any of the snapshot objects until that object is actually touched next time. This is nice because we have to get the metadata for that object anyhow next time, so making that update at that point is not only efficient, but it costs nothing more than we were already going to do since we had to update the object. This gives us the ability to have instant snapshots, fractions of a second for cooldown time before taking the next one, and is only limited by the underlying copy on write file system that we've already demonstrated up to tens of thousands of a snapshot per volume. So these are some really early results, mostly because I felt like it would not be a technical talk if I didn't show some. We are going to be putting our product through significant benchmarking now that we are past supercomputing, but I would encourage you to come to the booth afterwards to check them out in real time, because we do have this same test running in a loop there. So what we did, it's a relatively small test, but we took 32 OSDs of our Ultras, and 32 clients. We're scaling here from 1 client to 32 clients just to basically demonstrate some scalability of throughput, even as you add more and more clients and more throughput via the IOR benchmark. All of our OSDs and all of our clients are connected by dual 10 gig E, but there's nothing specifically limiting about that. We actually will probably ship by default with 25 gig E for Ultra. But there are a variety of technologies, since we're using commodity off-the-shelf hardware, that we could deliver. We only use a single volume. We're using RAID 6 Plus erasure coding. The test is IOR, which most people are familiar with, but just to give you some specifics, it uses the message passing interface to communicate across tasks. Each task is writing their own 10 gig file, and there's 32 per client. So we scale from 32 tasks to 1024 by the end when we're using all 32 clients. We perform full unmounts and remounts of the direct flow client in between the write and the read test, just so there's no caching, but we're writing 10 times the RAM of both the clients and the OSDs anyhow, so this shouldn't matter. It's mostly for thoroughness. So as you can see here, we scale from 1 to around 24 until we're basically maxing out the hard drives at that point, and then it starts to level off. But while we're scaling and the hard drives haven't fully saturated yet, we are getting very nice gains as we add clients, network throughput, essentially, to the realm. The write and the reads perform very similarly. There's a slight divergence around 18 to 22, but then they come back into line. That's mostly due to the stripe unit size we happen to choose for this experiment. But we are quite happy with this result. This represents a 2 to 3 times improvement for this specific setup compared to our previous product in the rack units, but individually per OSD we're about 8 to 10 times faster. So conclusions. With Ultra and the release it will come in, Panasas 8, I'm not a marketer, but I really do think this represents a new era of innovation and performance for Panasas file system. We're portable finally. We've decoupled the OSD software stack from the OS and the underlying physical hardware. We're using commodity off the shelf, so we can move quickly as that market changes and as our customer workloads change. We're using internal tiering extensively, even more than we did before, and we're significantly denser per OSD. We're separating metadata and data in a novel way that I don't know anyone really is in the commercial space right now, and using novel algorithms to boost both of those speeds. And finally, we've treated snapshots in a truly first-class manner with Ultra, and we're looking forward to how our customers enjoy them compared to our old snapshots. Especially from the internal side, we're excited about the ability to deliver more features and functionality in the high-performance parallel file system space, because we're able to offload some of that physical hardware development and kernel file system development by moving to COTS and the open source software within the OSD. But as I like to say, never trust slides. So we have that demo going. You can come poke at the realm in real time. We're in booth 1613, and I'd love to talk with you.